Okay, we're still trying to get to do more work integrals. We're doing vector calculus, integral vector calculus, work integrals. We're going to get the Green's theorem. And before we could do Green's theorem, we got to review double integrals. And we did the basics of it. I don't know if I explained it super well. This little this little area down here, say, you knew the area of that little chunk, multiply that by the height, which means going up to the value of the function at that point. That gives you the volume of a parallelepiped, a little differential parallelepiped. That would be like this. This inner part here, the value of the function times the area is the volume of that parallelepiped. That's a little differential thing, and then you sum over all the area in the xy plane, then you get the volume under the surface. That's what the double integral does. Went through this stuff. Sometimes it's more convenient to do your double integral in polar coordinates. Basically, when the region of integration is round, circular to some extent, or at least round. It doesn't have to be circular. I'm sure you've seen this derived in basic calculus. What polar coordinates mean is x equals r cosine theta, y equals r sine theta, which means r equals square root of x squared plus y squared. And the differential area isn't just r or dr d theta. Turns out you need a so-called extra r. Not really extra, it just comes out of the derivation. You can think for an area, you need a length times a length, right? To get the units right. Well, along r, that's a length. But along theta, that's an angle. You need to multiply theta, the angle in radians, times r. Then you get a length. So that's one way to help you remember the extra r. The dA now becomes r dr d theta or r d theta dr, depending on the order of integration. But if you look at it, now you have, especially this way, r d theta is a length, and then dr is a length. So length times length, which is area. We're still going to iterate the integrals, and you can do it either over dr first or theta first. Let's do an example. Find the volume under this surface with these boundaries. A little thinking, you could see that this surface is a sphere, or it's spherical, and the sphere has a radius 4. This boundary is a circle of radius 1. This boundary is a circle of radius 3. Both those radii are less than the radius of the sphere. So what you're going to actually be integrating over, the region of integration, is this annulus. Sphere is in the third dimension, and it hits the xy plane at a radius of 4. These boundaries are within there. So this is region of integration. Now you need to think in terms of what are the limits in polar coordinates. Well, it goes all the way around. Theta is just 0 to 2 pi. And r will go from 1 to 3. So I can integrate over r first. And oh, by the way, what's the integrand? Well, x squared plus y squared is r squared. So 16 minus r squared. That's the integrand. Extra r, all this, r dr d theta, is the dA. dA is the generic area, however you come up with it. In the limits, r goes from 1 to 3, and the angle goes from 0 to 2 pi. And this is a case where we don't have to iterate the integrals. We can split them up. This integrand, you have part of it's just a function of r and part of it's just a function of theta. The theta part is just 1. The other part is this. I won't go through how to take those integrals, but that's how you do it. This guy, you're given the problem in rectangular coordinates. Draw what that means. Integrating over x first. One boundary is x equals 0. That's easy enough. Draw that straight line. What is this boundary? X equals square root of 1 minus y squared. Well, square both sides, you get x squared equals 1 minus y squared, or x plus y squared equals 1. A circle of radius 1. So another boundary is a circle of radius 1. And y goes from 0 to 1. So draw that line, draw that line. Region that's enclosed by those 4 boundaries is this part here. To show you that it's easier to do in polar coordinates. So now, let's see. R will just go from 0 out to 1, and theta goes from 0 to pi over 2. Right over R first. R goes from 0 to 1, theta goes from 0 to pi over 2. Don't forget extra R. I took off points for that. 3 points out of 10. Copy mistake, just don't do it. And this is another case where we don't have to iterate the integrals, we can just multiply them. This one's actually fairly easy to do. I won't go through how to do each. Another case, given to us in rectangular coordinates. It's kind of tough. I should have drawn it here, but you look at these limits. This lower limit, x equals y, it's just a straight line at 45 degrees. This upper limit, again, is a circle, radius 1. And this upper limit on y makes everything nice. All you're looking at is a sliver or a piece of pie that goes up to 45 degrees, a radius of 1. So this in rectangular coordinates becomes this. R, well, let's see. Let's look at the integrated. Y squared, remember y is r sine theta. So y squared is r sine theta squared. This denominator is just r. That's the integrand. This is the dA with the extra r in it. And r will go from 0 to 1 out to the circumference. And theta goes from 0 to pi over 2. A slice of pi. It would have helped if I and you don't have to iterate. You can split it up as a product. I did need to use a table for sine squared, but I'm not going to do the individual integrals. The big thing is getting the limits. You think it's easy, but it's not that easy. This example isn't a polar coordinate example. It's just an example of complicated volume. You have to do some 3-dimensional thinking for this one. Volume of a solid bounded by these equations, all in the first pocket. X is greater than 0 and y is greater. I want to go through this. Here's one boundary, z equals 1 minus x squared. That is all these little parabolas. So it's kind of this tunnel type thing. The other boundary is z equals 1 minus y squared. That's this other tunnel aligned with the x-axis. This first tunnel is aligned with the y-axis. This is aligned with the x-axis. And let's see. X equals 0, y equals 0, and z equals 0. kind of have to think of the intersection of those two tunnels. Here is the final surface. A little weird looking. This takes some three-dimensional thinking. I can't quite explain every step. And what happens is you need to break up the region of integration. It's because it goes up to one surface, one side of this line, x equals y, different surface on the other. So you're going to have to split it up into two integrals. This turns out these are functionally the same integral. So once you take one, it's just an example that sometimes these things are hard to understand. You have to think through it. Don't rush through it. Don't think, well, just quickly jot down some limits to my integrals and start evaluating integrals. Get the integrals set up correctly in the first place. At least by the time I taught this course, I expected you to be able to take an integral. The important part is getting it set up correctly. Done with the speech. So now that we've covered double integrals, the next video we'll get into Green's theorem. Back to work integrals.